now that we have actually constructed a general idea of a template, how is the flow being trained, sampled, and how we can actually train on discrete data by dequantization, we can now finally look at what F our invertible functions can be in a flow. In deep flows, especially also here for images, the common layer to use is a coupling layer. Coupling layer has been proposed in 2015 by Din et al. And the idea is quite simple because we can use here neural networks to really enable us very complex changes. So imagine you have now given input, which would be here X, although if you go through the layers, right, you can say it's also Z1, Z2, Z3, and so on, actually with different layers. But let's assume here our input is Z. In the coupling layer, we first split Z into two parts, which we call here Z1 and Z2. The first part, I just use the identity mapping. So basically, this Z1 here, I don't change at all, and this is my output of the invertible function. While Z2 here, I say, okay, I do transformations on it based on Z1. So I use Z1 here as input. Specifically, here we use a affine coupling layer, which just scales and takes a bias and shifts basically our different input set. So I take Z1 here as input to a neural network, which tells me how much should I scale Z2, and a neural network which tells me how much should I shift Z1 afterwards, Z2 here afterwards. And this is then our output. So there you see that I transform one part given the other part as input, while the other part is as an identity mapping through the layer. What is the benefit, or why is it so good? Well, because we can invert it quite simply, right? So I know that Z1 is exactly as the input of, as the output of Z1. So if I inverse the layer, I can use just again Z1 here as input to my two neural networks, and here I can just inverse the operations of adding and multiplication. Therefore, you see that it's very simple actually to perform this operation. The next benefit here is that actually these two neural networks, which model then the shift and the bias and the scaling, can be anything. So these neural networks don't have to be invertible because we don't need to invert these networks. We have the same input in the both forward and inverse path. This is a big benefit, as otherwise this log determinant of a Jacobian is hard to calculate. While here for our coupling layer, as we have a triangular matrix as LDJ, we actually just have to consider our diagonal. So therefore our LDJ is also very simple to calculate, namely just by the sum of the log of our scalings here. So the benefit of this coupling layer is, one, we can use arbitrary strong neural networks in here. Two, that we have a very easy time to do a forward path and the inverse path. And three, that we have a very easy time also to calculate the LDJ. We can now implement it here in a PyTorch module. So what we have is a network. So actually this network of the scaling and the shift is shared, just for parameter efficiency. And we have then a mask here. So what does a mask mean? Mask is basically to say, okay, which of my whole input is used for identity mapping and input to transform the other part. This is easier to define a mask here because then we can swap between what we actually want. For forward pass, when I first say, okay, I mask my input and then push only this mask input through my network, get a scaling and a shift out. I do something with scaling I'll look at later. And then I say, okay, I only want to transform those inputs that I haven't had in my network, because otherwise we would actually be cheating and we would have to invert again our neural network, which is not very easy to do and often actually impossible. Then our whole operation is just shift and scale and the other way around. We can do then a bit better in the sense that the scaling, as you might have already suspected, can be between minus infinity and infinity, right, which we take an exponential on. However, it can be the case that for very deep neural networks this is unstable. This is why we use here a scaling factor So the scaling factor is here because we take the scaling we push through a ton h and perform something on it. So what exactly does it do? I try to visualize it below here. Depending on the scaling factor I have, I actually scale what maximum scale output I want to have. So what output should sigma have as maximum and as minimum? The idea is then that we start here with 1 and therefore limit our possible scaling, while in case the network really needs larger maximum minimums, we can learn it. But usually it's better to keep it low so that we have a stable connection first. As I said, we use the masking to decide which part of X should be masked and which one should be used to be transformed. The most common ones in images are checkerboard mask and channel mask. So what does that mean? I take here, let's say our input is 8 by 8 times 2 channels. The checkerboard mask here uses basically a chess mask. So in the sense that one pixel is not masked, the other one is masked, and so on. So over width and height, I do this alternating of masking, not masking, while a channel mask, for example, would go over channels. Say, okay, channel 1 is masked, channel 2 is not masked, channel 3 is masked, and so on. Throughout the network, we will always alternate the masks in the sense that the first pixel has been in the first flow masked, in the second flow it should not be masked. This is because we want to transform all the input. Right, and as we alternate then this masking, we are able to actually change all the possible inputs in our network, which is very efficient and still helpful. Below here then I just define a neural network which will serve our purpose of modeling the mean and the scaling. And the details here are not relevant. In case you're interested, you can look at it. Basically just similar to ResNet with some tricks, which I took here as inspiration from one of the state-of-the-art models. Finally, we can look at the training loop of a normalizing flow. So what we are now building is a flow based on our coupling layers, on our dequantization. So if we input image, push it through a dequantization, couple of coupling layers, and have then as output our Gaussian distribution. In case we want to invert it, we would basically start from here and go the other way. So this is basically what I create here as a flow, as a function. And I want to test out actually as an experiment what happens if we use variation dequantization and what happens if we don't use it. We again here just have a training function, which is not too important as we have already seen it a couple of times for the flows. And therefore, we just use here PyTorch Lightning to simplify everything for us.